Okay, topic 6 now in chapter 1, transformations of functions. Here are the objectives, and again, some of the key words here. Recognizing graphs of common functions, vertical shifts, horizontal shifts, reflections, vertical stretching and shrinking, horizontal stretching and shrinking. All right, almost sounds like some kind of weight control program here. And then graphs involving the sequence of transformations. Let's go on. Now, when we think of functions, there are a number of common functions. And I suggest you make a list here of this. So whether there's room on the right or left, wherever you're taking notes, let's make a list of these. So here, the first function, and there are 7 major ones, is just the function of a constant. Here, the function is just going to be equal to x. Here, the absolute value of x. Here, x is going to be squared. Here, x is the square root of, and cube x, and the third root of x. So what we'll do now is we go through a series, and again, you're watching this, you're looking at it, you're tying it in, picking up on the points that we mentioned in our lesson. So number 1, and I think it's probably a good idea to label these as the numbers so we get some kind of way of referring to them. This is the constant function. Now, again, this is y equals c, or we can think of it as y equals b, which is our y-intercept, which is what they've drawn here. Whatever value that would have been is going to be a horizontal line. So what is the domain? Well, the domain of this is it's going or coming from negative infinity to positive infinity is written in interval notation this way. So you want to write domain of this function, a little sketch, and this is the constant function. Build up your vocabulary, is this. Now the range, that would be its y value, is whatever that constant was, whatever that b value would have been, or they're calling it the constant here. Now, the function of the constant is this, which is its domain, and it's even. Again, some points to pick up. Now, for number 2, this function is known as the identity function. So domains of an identity function, as we see it here, and this is like y equals x. So the slope would be 1x, and the y-intercept would be 0, and the graph then would go through the origin over 1 up 1, and the line would look like so. Now again, there's arrows on the end. This goes to negative infinity for the x values, and out this way to positive infinity. So again, domain equals negative infinity to positive infinity. Now the range, again, this is coming up from negative infinity going up to positive infinity. And the function, as we look at it, is increasing in this picture for this value. And the function is odd. Now, as we go to the third major function, f of x is equal to the absolute value of x. Notice if we took away the absolute value signs, we'd get y equals x. But again, our y values always had to be positive. So in a sense, it's starting here at 0 and then shooting up this way. But for absolute values, it also could have been a negative x. So again, this is positive slope of 1. This would be a slope of a negative 1, which would go this way, negative slope. And we end up with this V-shaped form. Now, what would be the domain of this V shape? Well, again, this is going off to negative infinity in this direction and positive infinity in that direction. So the domain of this function is, in interval notation, parenthesis negative infinity to positive infinity. Now, what's the range? This is y values. Well, we know it's starting at 0, and then these will be going up to positive infinity. So since 0 is included in a specific point, we use a bracket, comma, positive infinity for the range. Now, the function is decreasing on the negative side from negative infinity down to 0, and it sort of just approaches 0. So let me erase that so you can see it better. So its interval notation for decreasing function would be from negative infinity to 0. Remember, this is going out to negative infinity, so coming down, it's decreasing until it gets to 0. And now just at 0, it starts going up. So it's increasing then at 0 to positive infinity. And the function is even. Now, this function is x to the second, which is the standard quadratic function. Anything to the second power we describe as quadratic. Now, these produce a parabola where if you were to put this in a graphing calculator, it would look like so. And the domain of parabolas when it's like this goes off to negative infinity in this direction, positive infinity. So there is the interval notation for this function, its domain. Now the range are y values. So this one also is starting at 0 and eventually will go up this way and this way. So again, bracket to indicate 0 is included in the set goes up to positive infinity. Infinity always has a parenthesis. Now, the function, as we see, is decreasing, similar to the previous one, until it gets to 0, and then increasing from 0. Now, notice 0 is not included here. So it's just the side of that little infinitesimal spot, and then the other. All right. And the function is even. Let's go on. For function 5, we're asked to graph the square root of x. Now, again, if you had a calculator, if you did a t-chart and got some points, the graph would look like starting at 0 and then shoots off like so. So what would be the domain of this now? Well, it would start at 0 and 0 would be included and goes to positive infinity. Now the range of the function would be y values, and it's the same. Starting at 0 and going to positive infinity up this way. Domain this way, range this way. Now the function is increasing, starting at 0, and it's just beyond 0 now. 0 is not included, and then to positive infinity. And this function is neither even nor odd, going back to an earlier part. Now, the function of item 6 here is that x is cubed. Again, putting that in a graphing calculator, you get this nice wavy line. So the domain of this function, again, it's going to negative infinity, positive infinity for the x values, it's written right there. The range, the same, coming from negative infinity to positive infinity. And the function is always increasing. Now you might think it's leveling out here, but there's an infinite number of points here, and they're all so slightly different, so that it is increasing, and the function is odd. Let's go on to our, and number 7 now is the third root, or the cube root of x. Again, the graph looks like so, and interestingly has all the same values as x to the third for domain, range, function, and the function is odd. Take a moment, a little sketch will do you, and we'll go on. Okay, here we're going to illustrate what is called a vertical shift. Now, if you remember this formula, and we said that if this were the line, and this was our original y-intercept, and we changed the y-intercept by either making it greater or less, it would move this line up, and it would become like parallel lines to it, up this many units to a new y-intercept, or down to a new y-intercept. The general shape of the line would stay the same. Well, that's what they're showing here. Here is a function that they're indicating by this black line, and then they're shifting it by a plus c. So whatever value the c would be would shift that. And notice it's going from this intercept to that intercept. The general shape of the function is the same. Now, if you had a negative value here, it would just take it from where it was to move it lower, whatever the values are. So this is showing what vertical shift looks like. Now, that was all background. So now we're going to do example 1, and be sure to include this in your notes. So here we have that function, which I believe is the third function of absolute value. And if we just did this part, that would be the blue line. But now we're going to shift it up vertically by 3 units. So there is our original value, which would have been plus 0, which should be the origin. We're now going to shift it up 3 units, and our new value is the red line. This is the vertical shift of absolute value. Now, everything was pretty standard so far, but on horizontal shifts, gets to be a little tricky. So I put like a little star here to be especially noted what we're going to be doing. So what we have here, and this is the tricky part, our black line is our original function, but we're going to horizontally shift it. So it would look like this, and it looks like we're going to shift it plus 3 units, or C units, I should say, whatever that value is. Now, the tricky part of it is if it says plus 3, we're actually going to shift it in a negative direction. So, in a sense, we might think of this as our x-intercept. Now, let's say our x-intercept here was 3 or whatever number. This was a 3 here. We're going to shift it this many units over. So this c would be a 3, x plus 3. Now you would think, since it's a plus 3, you would move it this way. But that's the tricky part. It's not that. It's the opposite sign of this. It's going to move that intercept, that x-intercept, over 3 units this way. So whatever that constant is, I'm just using 3 as an example. So horizontal shift takes it horizontally, the opposite sign of what you see here. Now here it's showing a negative c. But if this were 3, and then we're moving it over 3 units this way, that would be x minus 3. The shift would move it positive to this point. That's the key to horizontal shifts. It's the opposite sign of what you see here is the direction you're going to move it as you shift it. Now, the nice thing of all these slides is that you can go back and now here we're going to another example, example 2, horizontal shift, but now we're doing f of x equals the square root of x, and we're going to shift it to the square root of x minus 4. Now, again, when we did this, the graph was this blue line, but let me prove why it's the opposite sign of what you see there. So under this radical, you can have any number that's lower than 0, that is any negative value. So what would be the value of x that you could have here? Well, you would equate this to x minus 4 is greater than or equal to 0. So when you solve this, you get x is greater or equal to 4. So now this is your new x-intercept, which is at 4. 1, 2, 3, 4. So the result then of shifting this horizontally is the opposite sign of whatever that number would be. So here it's a negative 4, so we're going to shift it horizontally to a positive 4 x-intercept. Let's go on. Now here we're looking at the reflections of graphs about the x-axis has this formula, and this, notice that here it's the negative and this would be the positive about the x-axis. And the reflection on the y-axis, here it would be this function. Notice x is negative and here x is positive. So again, pause, take some notes on the formulas, and now let's see what it looks like. So for example 3, we have the cube root of x, and then the cube root of negative x. Now the cube root of x would be this blue line that we see here. And the cube root of a negative x would be this red line that you see here. And notice that the y-axis here could have a special name here that we'll mention, and just to give reference to it, happens to be the axis of symmetry. And you might add that word, those words, so that if you fold the graph along the y-axis, one part would overlap the other. A good idea of reflection, that you're getting the same image but sort of on the other side. Okay, again a little sketch of this. More background information on vertically stretching now and shrinking of graphs. As we look at this, we see the blue line was the original, and then this sort of purplish red here is the stretching of that, while in this case, again, the blue line is the original, and then shrinking that blue line, and this is the illustration of it. And here we're saying that C is greater than 1, and then now C is less than 1, but greater than 0. So part of it is visually experiencing what these words are like in regard to function. Now in example 4, we're seeing vertically shrinking of a graph. So our blue line is this absolute value of x, and if we put a 2 in front of that, and remember if we had here y equals mx plus b that I've written out here actually, what's the slope of our first line? Well, this is the slope of 1. Now, when we put a 2 out there, that's going to be a slope of 2, and that rises up, gets closer to the y-axis. So from its broader position in blue to its closer shrinking of position in red. This is, I think, a good example of vertical shrinking of a graph. So in this slide as background, again, which is stretching, which is shrinking? Shrinking is getting closer to the y-axis. As you can see with the blue, the original, then we get closer with the reddish purple there. That would be shrinking. C is going to become greater than 1. As the numbers get larger, the line gets closer to the y-axis. That's shrinking. Now, stretching is where the C value is greater than 0 but less than 1. And we see the purple line getting further away, in a sense, from the blue line, which was our original. All right, we're almost finished. Now, in example 5, we're using graphing sequence of transformations. So let's kind of tie everything we've had together so far. So here is our basic parabola, which is this blue line right here. Now, we're going to move this new function from this original x squared up 3. So that would be this one right here. Now, internally, we have a horizontal transformation. This is a -1, so it's actually going to become a +1. So we move it over 1 this way. And then now we're going to stretch it vertically to a 2, which moves it closer to the y-axis, which is this one right out there. Wow, it's kind of jammed up, a little hard to see, but that's what we would do. All right, now for our last. So we're calling this example 6, but actually it's actually like 5a. We can call it 6, that's fine. So this is where we started originally. We moved up, then we went over 1 because of its opposite sign, and then we went to the actual process of moving it closer to the y-axis, the shrinking because of the 2, and this is where we ended up. So this one makes it quite clear. And this wraps up this rather complex and challenging